Okay, this is your video on heating curves. What we have right here is the heating curve for water. What a heating curve is showing, it's showing on the x-axis, it's how much heat is being added at a constant rate. So usually we have heat increasing as we go from left to right. And then on the y-axis we have temperature. So we're not necessarily using this graph to interpret any to interpolate any value, but I'm using it as a model to show you at what point different phase change is occurring, because heating curves show two things. They show phase change, but they also show just the heating up of a substance. So let's go ahead and take a look at number one, right? We'll look down the bottom right-hand corner, or left-hand corner, right? Number one is this is water, is below, if you notice, it's below 0 degrees Celsius, which means it's a solid, right? And whenever I see a heating curve and I have a diagonal line instead of a straight, a straighter line, straight horizontal line, that's showing that temperature is going to increase. Well, whenever we have temperature increasing, and we need to calculate Q, because that's what the whole part of this is, it's to calculate Q, I know that Q is going to be equal to mc delta T, a formula that we've seen before. So whenever we're dealing with changes in temperature, this is the equation that you need to use. Right? Now with number two, if you notice, there is no temperature change. Right? And the fact that there's no temperature change should be an indicator that a phase change is occurring. And obviously, if I'm looking at this curve for water, and anything that is at 0 degrees Celsius should be showing the melting or the freezing point. So I'm going from a solid to a liquid, or I'm going from a liquid to a solid. So at number two, I can't use Q equals mc delta T, because there is no delta T, there is no change in temperature. But energy, as you notice, is still being added. So the question is, where is the energy going? Well, the energy is going into breaking up the interactions, or the the attractions in between the water molecules in the frozen state. So in this case, Q is not going to be equal to mc delta T, but it's going to be equal to mass times delta H of fusion. Okay? So if I wanted to find out, for example, how much energy it would take to raise, say, if I had an ice cube at negative 10 degrees Celsius, and I wanted to get it up to liquid at 0 degrees Celsius, I would have to add up these two Q values, right? Now 3 is water in liquid state. Now, if you notice, I have a temperature change. Well, it means if I have a temperature change, I should have Q equals mc delta T, okay? And then that brings me up to the boiling point, which is up at 100 degrees Celsius. Again, with a phase change, there is no temperature change. So when I'm trying to solve for Q, when I'm going from a liquid to a gas, or a gas down to a liquid, that is mass times the heat of vaporization. Okay? And in this video, we're going to do some examples of calculating with the heat of vaporization and calculating with the heat of fusion. Right? And then lastly, with step 5, we have, this is steam, right? We have water and gaseous state, but if you notice, I am having temperature change. So Q is equal to mc delta T. Okay? Now, what you should realize is, earlier we talked about mc delta T, and for water it was always 4.184 joules per gram degrees Celsius. And that is true for water, but it is only true for water at the liquid state. Okay? So if I am to do, say, if I need to use mc delta T for step 1, or use mc delta T for step 2, I need to get the specific heat capacity for ice, and I need to get the specific heat capacity for steam. Okay, well, steam, or excuse me, ice's, which is at step 1, ice's specific heat capacity is 2.06 joules per gram degrees Celsius. And for steam, it is 2.02 joules per gram degrees Celsius. Okay. Now, I've seen it where they use 2.1 for steam or for ice, and they use 2.0 for steam. These are the values that we're using, so we're going to stick with these values. Not to mention, there's 3 sig figs there, which makes things nice, at least consistent, right? So, with that being said, I also need to identify my heat of fusion, and my heat of fusion is, which is the amount of energy it's going to take to either melt or freeze something times its mass, and that is going to be 334 joules for every 1 gram of the substance, in this case water, H2O. Right? The heat of vaporization is a little bigger, well, quite bigger, 2,260 joules per gram. All right? So with all of these values, we should be able to solve for the amount of heat it takes to raise any phase of water to any other phase of water at whatever temperature you want to go with. Okay, so now that you have those written down, let's go ahead and take a look at a problem. Right, so how much heat is required to melt 25 grams of ice at 0 degrees Celsius? All right, so if you notice, I'm looking at my problem right here, and I don't have any temperature change. And for me, that would indicate that I'm not going to use MC delta T. And I have other key words in here. One is melt, so I'm just talking about melting ice, right? And it's just ice that I'm melting. So with that being said, how much heat is required to melt 20.0 grams of ice at 0 degrees Celsius? When I refer to my curve, I am just here. I'm just at step 2. Okay, which step 2 is just heat of fusion. So, oops, wrong one. So I'll start off with 25.0 grams of ice over 1, and I'm going to use dimensional analysis for this. And I know that the heat of fusion was 334 joules per gram. Right? That means 1 gram, 334 joules. And remember, whatever number you start with is in the dimensional analysis problem, but you should probably finish with if you're dealing with sig figs. I'm left with joules. Okay, that equals out. Calculator. 334 times 25.0. I end up with a whopper of a number, 2788. Okay, apparently different colors too. 8900. What in this case I would definitely need only 3 sig figs. 1, 2, 3. I need to look at that next number. It just happens to be red too. To determine if I need to round that number up. I do. So that's 279. Right? And then I have 1, 2, 3, 4 zeros that go after it. So, how much energy does it take to melt 25 grams of ice at 0 degrees Celsius? It takes, 2,790,000 joules. Now, it's important that we realize we need to, since we're dealing with energy and our values are in joules, we need to pay attention to our direction of that energy. Well, when it comes to melting ice, and it comes to boiling water, those are both endothermic processes, which means Q is positive. When I'm going to be freezing or I'm condensing, okay, then those are exothermic processes. Okay, so keep that in mind. Let's go ahead and take a look at the next problem. Okay, so how much heat is required to raise 40.0 grams of ice at a temperature of 15 degrees Celsius to 140 degrees Celsius? Now there's a couple pieces of information here that we need to look at. One is I have 40 grams of ice, right? So I am in, Wait a minute here. That should be water. So let's go ahead and change that to water. A little typo there. So 40 grams of water at a temperature of 15 degrees Celsius, and I want to raise that up to 140 degrees Celsius. Now, looking at my curve, 15 degrees Celsius is right about here, which means I'm liquid water right now. And I want to know, right, how much to get to 140 degrees Celsius, which honestly is way up here. Okay, but anyways, I am steam. Here is liquid, so I'm gas up here. And liquid water, so we just have just regular old water. Well, if I'm going from here all the way up here, which is way up my graph, unfortunately, I can match, or I can identify how many different steps it's going to take for me to get to where I need to go. So for every time you finish a line, that's 1, 2, 3, which means this is going to be a 3-step process here. So I'm going to have calculated Q 3 different times, and then I'm going to add all 3 of those Q values together. So let's take a look. How do we do this? So first, I'm going to have 40 grams, and I need to, it's at 15 degrees Celsius, so I'm at liquid right now. So with my first step, okay, 15 degrees Celsius, I need to get that water, if you look at our graph, I need to get that water up to here, which is at 100 degrees Celsius. So I'm going to go Q equals MC delta T. Okay, and again, this is a endothermic process because temperature's going up, right? My mass is 40.0 grams times specific capacity of liquid water, which is 4.184 joules per gram degrees Celsius. And then I'm going to have a change in temperature. So 100, which is where boiling is, minus 15 is 85.0 degrees Celsius. So when I calculate that out, right, 40.0 times 4.184 times 85.0, I'm going to end up with a 3 sig fig answer of 14200 joules. Okay? So that's nice and handy dandy. Next step. Now that I'm at the boiling point, I need to boil the water to get it up to steam, because when we're looking at this stage right here, when we're looking at step 4, we don't have just water and just steam, or once it reaches the boiling point, it's steam now. This is liquid and gas. Both phases of matter are found at the phase change points. Likewise, if I'm over here at step 2, I should expect to see solid and liquid states of matter when the phase changes occur. Okay, so I need to know how much energy is it going to take to get from, if I'm right here, this is practically liquid water at 100 degrees Celsius. I need to get it all the way over here where I'm going to be at the gas phase. So how much is it going to take to actually do the phase change? So looking here, my second step is going to be Q. Now remember, at a phase change, there is no change in temperature, but since I'm dealing with since vapor is involved, so to speak, I use mass times delta H of vaporization. That'd be delta H of vaporization, which is the same as saying 40.0 grams, right? Kind of like dimensional analysis, right? Times, in this case, with the heat of vaporization, remember I'm boiling, it's not the 334, but it's the 2,260 joules per gram, right? Same thing as having gram over 1 right here, right? So my grams would cancel out, I'd be left with just joules. So 2260 times 40.0, I'm going to have 3 sig figs in my answer, and my number ends up being, well, I don't have to do any rounding, 90,400 joules. Okay? Now, right now, after the second step, I currently am at steam at 100 degrees Celsius, but I need to get steam up to 140 degrees Celsius. Well, that means I have a change in temperature. And if I have a change in temperature, I'm using Q equals MC delta T, which means mass 40.0 grams times the heat capacity of steam, which is going to be 2.02 joules per gram degree Celsius, times the change in temperature, in this case would be 40.0 degrees Celsius. Right? All my units will cancel out. I'm going to be left with, let's see, 40.0 times 2.02 times 40 again, 0.0. And I need 3 sig figs in my answer, so I'm going to end up with 3230 joules. Now, I'm not done yet. Okay? To be done, I need to add up all of those values. So my total would be, let's see here, 3230 plus 90,400 plus 14,200. And again, I'm following my sig fig rules. In this case, when I'm adding, there's no numbers to the right of the decimal, so you don't have any numbers to the right of the decimal on your answer either. 107,830 joules. That is the answer to the question. How much energy does it take to raise 40 grams of water from a temperature of 100 from 15 degrees Celsius up to 140 degrees Celsius? It would take 107,830 joules. Okay? So, that one's a moderate question, right? You're going to have one-step questions or two-step questions, three-step questions, and of course, you're going to have a biggie. How much heat is required to raise 250 grams of ice at a temperature of negative 15 degrees Celsius to 105 degrees Celsius? Well, I obviously know if I'm at 105 degrees Celsius, then this is steam. Okay? So, what I would like you to do is think to yourself, looking at my graph, right, how many steps am I going to have here? Right? I'm going to go ahead and clear all this mess here. Right? Now, looking at my curve, I'm starting at negative 15, which is actually below my graph, so right about here. Right, that's my starting point, and my ending point is way up there. Okay? So let's take a look at how many steps I'm going to have to do. I'm going to have to do 1 step, 2, 3, 4, 5. This is a 5-step problem. Okay? So that means I'm going to have to use, if you notice, I have a diagonal line right here. So I'm going to use Q equals MC delta T. And then I have a phase change right here. I'm going to use delta H of fusion times the mass. And then here I'm going to have MC delta T again. And then over here at the phase change, I'm going to have delta H of vaporization times the mass. And then up here, again, I'm going to have a change in temperature. I'm going to have MC delta T. So I'm going to have a lot of problems going on right here. Okay? So let's go ahead and try to work it out. So first, this can probably take 2 pages, or I'll have you write all the stuff down and make sure you get it before I erase it. First step, I'm going to go from negative 15 degrees Celsius ice up to the melting point, which is 0 degrees Celsius. So Q is equal to MC delta T. In this case, that's going to be 250.0 grams times, remember, the specific heat capacity of ice is not the same as the specific capacity of water, and that is 2.06 joules per gram degrees Celsius. And I'm going to multiply that by the change in temperature. In this case, would be 15.0 degrees Celsius. Okay, I plug in that. 250.0 times 2.06 times 15.0. I end up with a 3 sig fig answer because of the temperature of 7730 joules. Okay, I'm going to write kind of small because, like I said, I'm going to try to get it all in one line in one slide. 2. Q is equal to, now what am I doing here? I'm at this point I've given enough heat into the system to melt the ice, but now I need, or to get to the melting point, now I need to melt it. So this is going to be mass times the delta H of fusion, which is the same thing as 250.0 grams times 334 joules per gram. I work that out. 334 times 250.0. We end up with, well, in this case, we end up with only 3 sig figs because that's just how the math works out. 83500 joules. Okay, now at this point on the curve, I have melted all of my ice. Now I have liquid water at 0 degrees Celsius. I need to get it all the way up to the boiling point, which is going to be 100 degrees Celsius. So Q is going to equal MC delta T, which is equal to 250.0 grams times 4.184 joules per gram degrees Celsius times 100.0 degrees Celsius. All right, so I'm going to go 100.0 degrees Celsius times 4.184 times 250.0, and I'm going to end up with a 4 sig fig answer, which is going to be 104600 joules. Okay, now at this point, I've finished my third leg of my curve. Now I have water at 100 degrees Celsius. Now I need to boil it. And boiling is going to require heat of vaporization. M times delta H of vaporization, which is going to be equal to 250.0 grams times 2,260 joules per gram. Right? So 2260 times 250.0 equals, with 3 sig figs in this case, because that's all I have in here, is 565,000 joules. Now at this point, my fourth leg is done. I have boiled all my water, liquid water. It is now gas. It is gas vapor at 100 degrees Celsius. But I don't want it at 100 degrees Celsius. I want it at 5 degrees Celsius. So actually, my bad. I can put the little graph in there. I'm silly. Here we go. So we're going right about there. That's where we're going to end off. Right there. So, that being said, we're still going to use to boil, not to boil, but to heat up that steam, which a lot of people have a hard time understanding. You can heat steam up past 100 degrees. You can cool ice down below 0 degrees. Okay? It's, it's possible. Do it all the time. Okay? So step 5, since the heat is going to result in a change in temperature, I need to use MC delta T. Mass is 250.0 grams times the heat capacity of ice, or excuse me, of steam, which is 2.02 joules per gram degrees Celsius, times my change in temperature, in this case would be 5.0 degrees Celsius. My final number is 5.0 times 2.02 times 250.0 equals, I need to have only, in this case, I'm going to have 2 sig figs, which is going to be 2,500 joules. Again, I want to have my right answer. I have to add this value, this value, this value, this value, and that value up. So 2,500 plus 565,000 plus 104,600 plus 835,000 plus 7730. My final answer is going to be 763,330 joules. And again, heat's going in, so it should be positive. So in this case, in order to raise the temperature of 250 grams of ice from a temperature of negative 15 degrees Celsius all the way up to 105 degrees Celsius as steam, it's going to take 763,330 joules. Okay, so I know it looks like a lot, but it's all the same stuff. You just have to make sure you realize what part of the graph you're working on. Okay, the graph will help. The graph will help. Okay, if you have any questions, please ask.